You are writing a code, you allocate the memory, you read and write to the variables, and everything just works. But have you ever wondered, where does that memory really live? Who owns it? Or can you access everything in your RAM? And what happens if you cross the line between what you control and what the operating system controls? Welcome back to what every programmer should know about the memory. Today we are talking about the boundary between your program and the operating system. User space versus kernel space. This division is at the heart of memory protection, stability, and system security. And understanding it will help you to reason things about the segmentation faults, page faults, memory map, virtual memory layout, and why system calls are more expensive than function calls. Let's dive in. When your program runs, it lives in a space which we can call the user space. This is a protected region on the memory dedicated for user's program. You get your own private view of the memory, a virtual address space that is isolated from everything in the system and also other programs, and most importantly, from the kernel itself. The kernel, on the other hand, lives in kernel space. This is the privileged part of the memory, where the operating system code, device drivers, file system handlers, networking stacks, and system resource managers live. Only kernel can touch this area. Your application cannot access kernel memory directly, and that is by design. This separation enforced by hardware itself. CPUs operate in different privilege levels, often called rings. Your program runs in ring 3, the least privileged level. The kernel runs in ring 0. If you try to access the kernel address from user space, the CPU traps that access. You get a segmentation fault, and the system kills your process. This is how modern systems stay stable. One bad program cannot crash the system because it cannot touch the kernel. The split between user space and kernel space is there for a reason. Safety, control, and performance. If your user program had direct access to hardware or kernel memory, a single bug could override system data, disable security checks, or crash the entire operation system. By isolating the user code, the kernel enforces the boundary. You don't get talk to the disk, or the network, or memory map devices, unless the kernel says it's okay. But this split has its own consequences. Every time you need something from operation system, it doesn't matter if it's file read or socket send or something like memory allocation that needs to touch the disk, the CPU has to switch from user mode to the kernel mode. That is called a context switch. It saves your state, loads the kernel context, does the operation, and then switches back. And that's, as it sounds, is expensive. It can cost hundreds or thousands of cycles. That's why system calls are always slower than in-process function calls. So when you write performance-sensitive code, minimizing kernel interaction really matters. Buffered I/O, memory pooling, and batch system calls exist for a reason. You want to stay in user space as much as possible, and you need to know what tools you can use. Let's look at how memory is laid out in a real process. On a 64-bit Linux system, your program gets a massive virtual address space, but only part of it is mapped. Typically, the lower half of the address space is reserved for user space. The upper half is reserved for kernel. Within user space, memory is further divided into regions. There is a text segment where your compiled code lives. Then there is data segment for global variables. The heap grows upward. This is where malloc and new live. The stack grows downwards from higher address to low, and it holds your local variables and function calls. As we talk about the difference between heap and stack in this video or here. And there is mmap regions used for dynamically mapped files, shared memory, and large allocation. The kernel's part of the address space is hidden from you. If you try to access an address outside your user space region, the CPU throws segmentation fault immediately, as we said. On Linux, you can inspect your program's memory map using the /process file system. Run, for example, cat/proc/ the process ID of your program /maps. This shows you every region, what it's used for, its permissions, and whether it's shared, anonymous, or file back. When your program needs to do something that touches the system, like reading a file or allocating a memory beyond what's currently mapped, it has to ask kernel for the help. That is where the system calls come in. You invoke a sys call like read, write, mmap, or break, and the CPU performs the mode switch. Let's say you call malloc. Beyond the scenes, the allocator tries to fulfill that from the existing heap space. If it cannot, it might expand the heap by calling the break, or request a new region from the kernel using mmap. Mmap is a powerful system call. It allows you to map a file or a chunk of memory directly into your address space. It can also allocate anonymous memory, meaning memory that is not backed by a file. This is how large allocators like gmalloc or tcmmalloc handle a memory. They skip break entirely and go straight to the mmap. All these interactions go through kernel space, and while the data might end up in user space, the decision about where to place it, how to protect it, and how to track it happens in the kernel. Every time a page fault happens, say because you accessed a virtual page for the first time, the kernel steps in. It allocates a physical page, maps it, and resumes your program. That is invisible for you, but it is critical for the performance. One of the most interesting examples of kernel and user space interaction is what happens during a fork. When you fork a process, the child gets a copy of parent's memory, but the kernel doesn't actually copy all the data immediately. It uses a technique called copy on write. The idea is simple. Both processes share the same physical pages, but those pages are marked as read-only. If either process tries to write on them, the kernel steps in, copies the page, and gives each process its own version. This lazy approach saves time and memory. Similarly, when you use a shared memory, whether it's shared library, mapped files, or memory between threads, the kernel decides how to back those pages, who gets access, and when to synchronize writes to disk. Understanding between the user space and kernel space is not just theory, it helps you design better systems. You start to see why some operating systems are fast and some are slow. You understand why mmap is more flexible than malloc, why copy on write matters, and how memory protection works at the fundamental level. Your program doesn't run in isolation. It is a guest in the carefully managed environment. The kernel is your gatekeeper. It handles your requests, protects the system from bad behavior, and ensures every process gets a fair slice of the memory. If this episode gave you a clear picture of what's going on under the hood, hit like and subscribe to not miss the next videos. You can also drop your questions in the comment below. I'll see you in the next one. Good morning, good afternoon, and good evening. Bye.